We rely on gas to cook our meals and heat our homes, treating it as a quiet, domesticated utility. But the fuel inside those lines is incredibly dense. Strip away the steel, and you are left with a highly volatile form of stored energy, ready to expand instantly. To access this energy, humans must drill thousands of meters beneath the ocean floor. Deep underground, the gas is trapped in rock formations under immense geological weight, creating a pressure differential that can reach 10,000 psi compared to the surface. Taming that explosive geological force and safely packaging it into a portable steel cylinder requires some of the most rigorous engineering on the planet. The operation usually starts far offshore. Survey vessels send powerful acoustic sound waves down to the seabed. The returning echoes allow engineers to build three-dimensional maps of the sedimentary rock layers trapping the gas. To reach those layers, engineers connect hundreds of steel pipes end to end. They suspend this massive drill string from a surface rig, driving an alloy bit through miles of water and solid rock. As the drill cuts deeper, instruments scan the rock for porosity and permeability. Porosity measures the amount of microscopic empty space inside the rock, while permeability measures how well those spaces connect to let the gas actually flow. High numbers in both metrics dictate whether a $100 million well will successfully produce fuel. Breaking into a highly pressurized reservoir carries massive risk. If engineers mishandle the pressure differential, oil and gas can surge up the pipe uncontrollably. These blowouts result in devastating rig fires and environmental disasters that cost billions to contain. To prevent this, extraction requires a massive steel block called a blowout preventer, installed directly at the seabed. As pressure spikes dangerously, its internal mechanical rams instantly slam shut, pinching off the central drill pipe to hold back 10,000 psi of upward force. Drilling into the Earth's crust is a high-stakes mechanical battle to establish a controlled chokehold on the planet's natural outward pressure. Once the well is secured, the upward flow begins. What surges to the surface is a chaotic, toxic slurry of raw gas mixed with formation water, liquid hydrocarbons, and fine sand. On the platform, this mixture enters multi-stage steel separators. These act as the first line of defense, slowing the flow down so gravity and pressure drops can split the stream into distinct layers of gas, liquids, and water. The raw gas is then piped onshore for a process called sweetening. Here, chemical solutions strip out corrosive moisture and lethal impurities like H2S. Hydrogen sulfide, or H2S, is a naturally occurring gas that is highly toxic and corrosive enough to eat through steel pipelines. With the impurities gone, the clean stream enters deep cooling cryogenic systems. Inside these vertical fractionating towers, temperatures drop severely to separate the gas into its core components. The methane is kept in its gaseous state for the standard natural gas supply. The propane and butane, however, are compressed into a liquid form. This creates LPG, or liquefied petroleum gas. The violent slurry is now chemically purified and separated, but as a highly compressed liquid, this fuel still requires a flawless physical cage to remain stable. The standard gas cylinder demands strict metallurgical standards to function as a safe pressure vessel. Automated machines cut hot-rolled steel sheets into precise circular blanks and rectangular strips. Tolerances must remain within just a few millimeters, because any deviation directly compromises the cylinder's pressure resistance. These flat blanks are fed into heavy-duty industrial presses, where tens of tons of mechanical force stamp the steel into three-dimensional hemispherical domes. The formed components move to automated arc welding stations. The seams are fused at thousands of degrees Celsius, while sensors continuously track voltage and torch speed to prevent any porous gaps from forming in the weld. To prove the welds hold, every empty cylinder undergoes an extreme overpressurization test. Workers fill the cylinders with compressed air and submerge them in water. If even a microscopic bubble escapes from a tiny defect, the cylinder is rejected immediately. The surviving cylinders are blasted clean, coated with an anti-corrosion primer via electrostatic spraying, and cured in heated chambers. This finish shields the steel from environmental decay for decades of continuous use. A single microscopic flaw would turn this household tool into a deadly bomb, making absolute precision throughout the manufacturing line a non-negotiable requirement. At the filling station, high-pressure pumps force the LPG from storage tanks into the completed cylinders. Automated scales weigh each unit before and after, measuring the exact volume down to the gram. The filled units travel rapidly down an automated conveyor belt, passing through sensitive electronic leak detectors for one final safety check before entering global distribution. The cylinder sitting in a kitchen is the endpoint of a massive logistical chain. Its journey stretches back across highways, through chemical refineries, down steel pipelines, and straight into the dark sedimentary rock layers miles beneath the ocean floor. Turning the knob on a gas appliance is the final action in a much larger sequence. You are opening the last, highly engineered valve of a multi-billion-dollar global pressure containment system.